This is Unit 8, Video 8. In this video, we will talk about colligative properties. And colligative properties are properties of solutions compared to the pure solvent. So if you make a saltwater solution, what would the properties of that be as compared to just pure water? And these depend on the number of particles in solution, so the concentration of particles, and not the kind of particles, usually. So we're going to have to factor in how much do we have dissolved, and then determine what happens. And there are three big ones we'll talk about. We'll talk about the lowering of vapor pressure, the elevation of the boiling point, and the lowering of the freezing point. There is a fourth one called osmotic pressure that's used more in biology and relates more to cells, but it can also be thought of as a colligative property. So let's begin with the first one, the lowering of vapor pressure. Now, when you make a solution, you get solute-solvent interactions, so salt-water interactions, which then create an attraction for the water and make it harder for the water, for the solvent, to escape. So in pure water, say this is just water, you have a certain vapor pressure above the liquid phase. Now in a solution of water, say in salt, some of those salt particles are now attracting the water molecules, not allowing them to escape. And that's why the vapor pressure above the solution is lowered. So it's always lower. Now it says here the word non-volatile. Non-volatile means what you're dissolving, the solute, has to be, it doesn't easily evaporate. Otherwise this will mess it up, because if the solute itself easily evaporates, then it'll actually add to the vapor pressure above. So, but if you're using a salt, for example, a salt is non-volatile. It has a low vapor pressure to begin with. It doesn't have any vapor pressure. But if you were to use something like ethanol, for example, is a liquid. So if you dissolve ethanol in water, this will have an effect on lowering water's vapor pressure, but the vapor pressure of ethanol will get in the way. That's why the word non-volatile is used. But most of the time, using sugar, using salt, this effect is seen. So there is a law for this. There's an equation and a law. The law was named after Mr. Raoult, and it simply says that the pressure, the vapor pressure of a substance is equal to the original vapor pressure, this here means the original vapor pressure, times the mole fraction of A. Now, what the mole fraction is here it says XA is the mole fraction and PA is the normal vapor pressure. But XA is the mole fraction of the solvent, because what you're testing here, or what you're measuring here, is the vapor pressure of the water, for example, of the solvent. Remember, it's the vapor pressure of what's in the solution, not what's being dissolved in it. It's the vapor pressure of this substance that we're measuring. So this is the vapor pressure of that same substance. So this would be this is the mole fraction of the same substance. So if we're measuring water's vapor pressure, then we have to get the mole fraction of water, not of the salt in the water. And we'll do an example of this to really drive the point home. So let's do exactly that. Here is our example problem. The vapor pressure of water at 40 Celsius is 55.3 torr. What is the vapor pressure reduced to when 85 grams of propylene glycol is added to 340 grams of water at this temperature? So our new vapor pressure, so we'll do, this is the vapor pressure of H2O, will equal the mole fraction of H2O times the original pressure, vapor pressure of H2O. Now the original vapor pressure is 55.3 torr at a certain temperature. Remember, temperature has an effect on vapor pressure, that's why temperatures are given here. So what we'll have to do essentially is multiply this 55.3 torr by a fraction, this mole fraction, and that will reduce the vapor pressure of water down to some smaller value. But the mole fraction here is of water. You remember that mole fraction, essentially, as this in this case of water, is the moles of water over total moles. And that's how we determine mole fraction. So what we've got is, we've got 340 grams of water, so we can convert that to moles. Let's do that. 340 grams of H2O 1802 grams, as we've done plenty of times now, in a mole of water. So go ahead and do this in the calculator, see what we get. So we get 340 over 1802 for a total of 18.87 moles. This is of water. And now we can do the same thing to propylene glycol, because we need the moles of propylene glycol. So this is, we have 85 grams of propylene glycol, which is C3H9O2. This, by the way, is antifreeze. Propylene glycol is antifreeze, and antifreeze is added a lot to water to change water's properties. The molar mass, I think, is 7712. So let's verify that. You'll do 36.03 plus 909 plus 32, 7712. So 77.12 grams in a mole. So do 85 divided by 7712, and we get ourselves 1.102 moles. So not a very concentrated solution. And then we can now get the mole fraction. The mole fraction then of water, remember this is the mole fraction of water, will be the moles of water, which is 18.87, plus the total. So this would be 18.87 plus 1.102, like so. So if we do that, 18.87 divided by the total on the bottom, we should get a mole fraction of 0.94. Let's do 4 sig figs for now, 48. So this is the mole fraction of water. Now we can apply that and put that into our original equation. So that mole fraction, 0.9448, gets multiplied by the original vapor pressure, which is 55.3 torr. Mole fraction, by the way, does not have units, because you've got moles up here, you've got moles down here, the moles will cancel each other out. So it's a unitless quantity. So if we multiply 0.9448 times 55.3, what we realize is that because this is less than 1, it'll lower the vapor pressure, and that's what we need. And indeed we get 52.2 torr for our vapor pressure. So pretty simple. Really, it comes down to understanding what the mole fraction business is. And notice the mole fraction, the vapor pressure of the water now with the propylene glycol has been reduced. Not by much, but it has been reduced. And not by much because comparatively we really didn't add that many moles of the propylene glycol. Propylene glycol is miscible with water, which means you can actually make a really high concentrated solution if you would like to. And it's pretty non-volatile, so that's why it's used in applications of changing water's properties. Alright, let's go on to talk about the next two colligative properties. Here it says that non-volatile solid-solvent interactions also cause solutions to have higher boiling points and lower freezing points than the pure solvent. So in this case what we've got is, this is the original phase diagram of water, and this is the phase diagram that we saw in the previous chapter. Remember, it went like this. It was solid, liquid, and then gas. Now here in the lighter magenta color is the vapor pressure of the pure solvent, or rather it's essentially the phase diagram of the pure solvent. Remember, it looks like a Y. So this is, for example, water. This would be pure water. This is actually not water, because this slope is positive. It's negative for water. But we'll say that this is just some kind of solvent. Now, when you make a solution by adding a bunch of salt, what happens is you expand the liquid range. So the liquid range here actually goes a little to the left and a little to the right, which means now the substance remains a liquid under a lower temperature. Notice, remember, temperature is on the x-axis, and at a higher pressure, at a higher temperature, it remains a liquid, which means you have expanded the liquid range. So water, for example, when you make a solution from water, of salt or sugar, water will freeze at a lower temperature and it will boil at a higher temperature. And you can actually get the change in temperature, change in the boiling freezing point in this case. You can also get the change delta T of the boiling in this case as well by doing exactly that. And so here it talks about vapor pressure, how the vapor pressure got lowered. So you can also look at it from the point of vapor pressure. This point versus this point, the solution now has a lower pressure, has a lower vapor pressure, and lower freezing point, higher boiling point. So the big thing is the liquid range has expanded. And we're actually going to show you a few equations that deal with this. So the boiling point elevation constant or equation looks like this. The change in the temperature of boiling, this is the change in the boiling point, is equal to some K, this is a constant that we'll see in a minute, times cursive M. Remember, cursive M is the molality. Here. So what you do then, you simply multiply the molality of your solution times some sort of constant that's been determined previously, and that's how much the temperature goes up by. And this temperature then is added to the normal boiling point. So if it were, say this is 2.5, then the new boiling point is 102.5 degrees Celsius if it were water, pure water. The freezing point equation actually looks the same. The only difference is that you have a Kf, your constant is the freezing point constant. And then delta T here is actually subtracted from the normal boiling point. So if you had determined that the delta T here is 2.5, then your new freezing point would be negative 2.5 degrees Celsius if it were water, because water freezes at 0. And we're actually going to show you how the Kf's compare for different solvents, but realize that this is based on molality. The previous colligative property was based on mole fraction, this one's based on molality. But both of them actually involve moles, which moles is how much of your solute has been dissolved, how much do you have in your solution. And antifreeze, again here, works on this exact same principle. We want to lower the freezing point of the solution in the car. That way, in the wintertime, the engine doesn't freeze over, and in the summertime, doesn't boil over. So that's actually why antifreeze is a very important solution. So this is a table of comparing different Kb and Kf values. Good old water is first. So the normal boiling point of water, remember normal means at atmospheric pressure at 1 atm. And its Kb is 0.51, its Kf is 1.86. What I want you to see is that notice that the freezing point of water is affected much more than the boiling point of water. But this all depends on the substance. Ethanol, the other famous substance we've talked a lot about, has a Kb of 1.22, so more than twice that of water, and a Kf of about the same as water, about 2. If you have something like carbon tetrachloride, this has a Kb that is significantly higher at 5, and a Kf that's really, really big. Now, this is partly because carbon tetrachloride is actually nonpolar. Nonpolar substances can actually be affected much more than polar substances. And you actually see the same picture here with benzene. Benzene is also nonpolar. Notice its numbers are actually bigger than that of the polar substances. In fact, water being the most polar, the most hydrogen bonded type substance, it does not have a big effect, technically on its freezing point and its boiling point. So that's the idea. And we'll be able to use some of these constants in a few example problems here. We'll probably do it in lesson number 9. Now, to reiterate that these delta T does not depend on what the solute is. So whether you're dissolving sugar or salt or calcium chloride or magnesium chloride, it doesn't matter what you dissolve, but only in how many particles you've got. So this will actually be an important concept, an important example that we'll come back to in video 9. All right, we'll see you then.